test this. Beautiful, everything works. Cool, hi. Thank you very much for coming. So the talk that I'm going to go through today is how to accomplish functional programming in Kotlin. Kotlin is a language that has some niceties around functional programming, but obviously doesn't ship things like type classes and a whole bunch of other abstractions that are quite nice. I'm not going to go too deep into actually writing applications in this talk. There's a workshop afterwards that I'd love everyone to come to that goes through how to actually apply these things to a product. But what we will go through is how the tricks that make these things available to us are actually built under the hood. So this is kind of what I looked like 2 weeks ago. It's what I look like now. Pulled all of my hair out in nervous anticipation of this talk. Because it's quite daunting to get on stage at a pretty pro functional programming conference like this and talk about Java, the good parts. But of the people here, how many are using Haskell professionally in production? Quite a lot. How many are using Scala? A resounding show of hands. This is the wrong crowd to start asking you about Java and JavaScript and things like that, right? But in today's software landscape, it can be really tough finding a job using the languages that we actually love. Try and find a job using Idris, forget about it. Agda, Coq, TLA+, anything that has any kind of formal application to it, it's very hard to find work. And while Haskell and Scala are growing communities and are growing ecosystems, even that can be quite tricky to find. Mostly the landscape is Java, C#, and JavaScript. And these are the languages that we work in, day out to pay the bills. And then on nights and weekends, we go home and we use languages that we actually really enjoy. So, nope, one sec. Yep. So you might know someone in this situation. You might be in this situation. And if you are in this situation, you should know that it's not all or nothing. It's not, on the one hand, Haskell and all of the nice abstractions that come with it, and then on the other hand, JavaScript day in, day out. There are middle grounds. There are things that we can do to make some of the tools and abstractions from a proper functional programming language available to us in whatever we happen to be using at the time. So the company that I work for, Ordermentum, kind of made a switch a couple of months ago. We were a Node.js company with all of the pleasures and pains that comes with. And a couple of months ago, we made a decision to switch away from that. The language that we chose that we ended up with was Kotlin. I had a whole big spreadsheet of probably 5 or 6 dimensions of language choices between Haskell, Scala, F#, everything. OCaml, Reason, the whole shebang. Kotlin won out from an ease of building a team. You can get a Java developer productive in Kotlin in a couple of days. It's a great power to weight ratio. It's very easy to roll out. But it's missing a bunch of things that I really look for in a programming language. So we might not always be lucky enough to be using Haskell. But as they say in the classics, you can't always get what you want. But if you try hard enough, sometimes you can get what you need. And this talk is basically how to do that. So I'm going to run through some syntax stuff with Kotlin very quickly, just enough so that with the examples that I'll show later on are a bit more obvious. Like I say, this is not going to be a talk on how to solve problems in Kotlin. This is going to be a talk on how to solve problems with Kotlin, i.e. problems that the language has. It's going to be how to do that at the value level rather than at the compiler level to improve the abstractions available. But there is so much syntax sugar, it's very calorically dense. So Kotlin as a language ships 2 ways to bind variables. We have val and var. Val is immutably bound by default. Var is mutably bound by default. It ships some immutable data structures. It also ships a bunch of mutable data structures. Nulls are explicitly handled in the language. This is actually a really nice feature of it. So unlike Java, which has null pointer exceptions everywhere, Kotlin will give you null safety of a kind. The functions themselves are first-class functions. They're available on classes and objects, as well as by themselves. So functions can be declared as either statements or expressions. If declared as a statement, you use the fun keyword. If declared as an expression, you use val or var and declare it as a lambda. They can be generic. They can be passed around by either construction or reference. So on this slide, we have the function not, which is generic in A, takes a function and calls it. We then provide not odd underscore, and not odd double underscore as 3 ways of showing how you can pass functions around. The first one, we pass a function by construction. We construct a function as a lambda in the function call. Second one, we use a syntax sugar where if you have a function that has a single parameter, Kotlin will auto-bind that parameter as it inside the scope of the function. So you have a couple of really nice things like that. And then finally, you can actually just pass functions as first-class citizens. Classes, the same as Java. we get rid of getters and setters and instead use val and var as bound parameters to determine whether or not it should generate a getter and setter or just a getter. We allied the new keyword, and default visibility is that all parameters are public by default unless you make them private. All classes are final by default unless you make them open. So it's quite a nice set of defaults. Data classes are a special case. They automatically derive a couple of helper methods around equality and serialization. Sealed classes are what we're going to see a lot of today. They're effectively the language's approach to algebraic data types, kind of. Sealed classes are similar to Scala, I understand. They can't be inherited outside of the file scope. So effectively, the compiler can tell, based on where the sealed class is defined, all of the constructors that can actually build something of this type, which means later when you're doing pattern matching, it can infer exhaustiveness at the call side, which is quite cool. Interfaces are just like Java's. There's nothing interesting there. As nice as the language is to kind of come to, wouldn't it be nice if we could do something like this? As nice as all the sugar and everything is, it'd be nice to be able to say, I take a generic f, and f is generic in another type. You can't do this in Java. You can't do this in Kotlin. The compiler will say you cannot apply a type parameter to a type parameter. F of a is illegal. End of talk? Not really. So there's an excellent paper by Yallop and White, I think from 2014. The title is Lightweight Higher-Kinded Types. And it's a very Haskell and OCaml-centric paper, but effectively it centers around an idea called defunctionalization. And the idea is that you can actually apply higher-kinded types to a language that has no idea what that means, as long as you're happy to pay two, depending on how you feel about your code base, small to medium prices. And the idea is that you can make ad hoc polymorphism available post hoc, which is a pretty cool idea. So we call this typed defunctionalization. Defunctionalization is old. 1972, I think John C. Reynolds was the first person to talk about it. But the idea is it was created at a time where functional programming languages were very popular, but the interpreters that you mostly ran these things on were very slow. And one of the slow bits was taking a higher order function, finding the call side of the function, figuring out what to do with it. It was a slow transform. So we came up with this compiler optimization, where you read a program that is written as a higher order function, as a higher order program, and then build this whole set of transforms that turn it into a single order program. And it's a compile time technique. So it's not intended for readability, it's intended for optimization of performance later on. So I'm using a quasi-OCaml syntax for this because you need GADTs and Kotlin doesn't have them. So don't worry too much about the syntax of this. This is just to show the idea of defunctionalization. We can define a method fold. Fold is a recursive function. It takes a function from A to B and returns a B. It takes a B and it takes a list of A. So it does the classic fold, reduce, whatever you want to call it. Now, using this base function of fold, we can define things like sum or add that have these operations on list. This is the standard functional programming, pass a function to a function and do a whole bunch of stuff with it. But if we're working on an interpreter where that can't be done, we need some way of expressing this. So we start by defining a type called arrow. Arrow is a GADT. On the left-hand side of the GADT, we define things called brands. Brands are just the constructors for the data type. They'll be used later by a function to determine what operation to run. On the right-hand side of the GADT, we have the type arrow, and we say that the types of the GADT are a tuple and then a value. And the tuple is effectively the pair of values from input to output that the function will have to implement. So we enforce what the function that is going to be used and created by these brands are at the time of construction of the brand itself. Now that we have this big list of things that we say everywhere in our program, we have a function that does adding, we have a function that does plussing, we have all of these higher order functions around. We now define a method called apply. And what apply does is it effectively pattern matches over all of the potential constructors of the arrow type, and it takes the higher order functions that were defined in place, replaces them with the brand that says what type they were, and an invocation to apply, and then apply does a lookup basically in this big dictionary of, that was a plus, okay, let me go find the function for a higher order plus. That was a cons, let me go find the function for the higher order cons. So we can now replace the compiler will replace, at compile time, any reference to a higher order function with an invocation to apply with the brand and the arguments. So now we can replace our recursive fold function with something that is not a higher order function. This is an ordinary function. It takes a brand, the type arrow AB, it takes a B and a list of A, and it returns a B. Now we see here when we get into the recursive portion where we actually iterate over the list, we call apply. We don't call the function that we've been provided. In the first position, we pass apply the brand, and then we apply whatever it is that we need to do. And you can see that here now, when we invoke sum or we invoke plus, we invoke it with the brand of the operation that it should be using. So previously, where sum would add numbers, this time it just makes a call to fn plus. Apply does a lookup on fn plus, finds the function that adds two numbers, figures out how to tie it all together. Compile time operation. But we're not here to talk about higher order functions. That's a problem that's been solved for quite a while. So instead, how do we apply this to types themselves? Well, the implications become a bit more apparent when you think about what a functor as an interface on the JVM kind of looks like. We want to be able to say, here's a functor, it's generic in some type f. F is generic in some type A and B and whatever else that we're going to do with it. It doesn't care about the container. And this is an operation that applies to things of that type. We'd like to be able to define ID as something that implements this, and here is its implementation of it. Now, Kotlin doesn't support this at all. There's no way to write this. This will not compile. You can't do anything to make it compile. Dreadful, right? So the thing that a lot of people do, you see this a lot in OCaml with the module functors, you see this a lot in Java and Kotlin and everything, is we monomorphize by hand. So we write an int functor and a string functor and whatever else, and then it's our job to pass them around by hand to whatever parts of the program we're using. That gets really old, really, really quickly. We write code gen, but now we're just writing compilers ourselves for the sake of using compilers ourselves. We give up and we go and use another language that supports the things we want to use. We don't have to give up, though. So the paper, Lightweight Higher-Kinded Polymorphism, shows us a way that we can actually express this. Take the generic f of a and lift it up once into another interface. So we define an interface kind, and kind is said to be generic in f and a. And effectively, all kind is like a single value map between the wrapping container type and the inner type. So we have f of a represented by kind f of a. We create a private constructor for ID, and effectively all this is a brand. This is how we'll do a lookup later to tell, should I be able to execute this function in this context? The brand is constructed privately, which means nothing in the program can actually construct one. And so the only way that you can possibly have a value of this brand is from a function in this file. We then define a type alias. This type alias is just so that we don't have to type kind fa everywhere. The type alias gives us a value ID of and generic in A, and that maps over directly to kind for ID A. So it's just sugar. Kotlin loves sugar. And then finally, we define a method fix. And this is the part, one of the prices that I was saying you have to pay. There is no good way to go from a kind of for ID and A into an ID of A. There's no transform you can write that the type system will recognize. Because if we could do that, we just have type classes. We don't need any of this. So we use an unchecked cast. Yeah, a lot of winces, a lot of like, I know. But this is the only price you pay to have this everywhere else in the program. Now, obviously, what this opens up is that pretty much anything in your program can say, hey, by the way, I'm a functor, I promise. I'm an ID, it's all fine. But you have this already. This is already a price you pay with whatever language you're using. The value of this is that as long as you are not a malicious actor, nothing in your program can be cast from a kind to an ID unless you use the method that is defined specifically for this case. Finally, we define our class ID, and we say that ID implements ID of. That is, that ID can be cast into kind f of a, where f is for ID. So we have a new type class now. We have a type class functor. Functor is generic in f, and we've replaced where we would normally say and f of a dot map is a function. We replace that with saying kind f of a dot map. And what that does is effectively allows us to say, if something says that it implements functor, define a method on a value that says that it is of kind f of a called map, and this is how it operates. So we've defined our map for functor, our f map, depending on which language you happen to be using at the time. We then define our class. So we say our class ID implements ID of, and we define a companion object, and we define a concrete implementation of the map. So we have in our ID function, we have a concrete implementation of map. The value, the class is of ID A. We define a method from A to B. We destructure the ID and take out the value. We apply it to the function. We rewrap it in ID, and now we have an ID B. The next step is we define an interface for the particular ID functor instance that implements functor. And we make a reference inside that to say, this ID functor instance uses the ID class and uses the map method on that. And the way that we can see that is inside the functor instance we call fix, right? Remembering that fix is that method that takes us from a kind f of a to a concrete implementation of whatever that class is. The functor instance and the plumbing that happens to make this all tie together is how it does dynamic dispatch to find where the right fix function is. If it can't, it can't find accidentally the wrong fix function. If it can't find a fix function, it will fail to compile. So you actually have compile time safety of I have written all of the instances that I need to. And then finally, we define a companion object. Companion object is kind of like static in Java. Defines something that we can say, this is a context that will give us a functor interface. And the way that that's useful is in the next slide. So in order to use these things ad hoc polymorphically, we actually need something called a witness. This is the second price you have to pay at the moment, although hopefully not for much longer. Because we didn't define the method in this slide, we didn't define map on ID A from a functor perspective. We defined it on kind FA, which means there's no way to have an ID and say, hey, by the way, ID is a functor and ID has .map, because then we have type classes. So what we end up needing to do is to say, here is something that gives ID all the methods that a functor needs. And here is something that here's an ID instance that can take those methods, extend itself, and use those methods. So a witness or evidence or whatever you want to call it is effectively a function that contains some way of decorating the value to say, give this thing the methods that it needs. And I'll go through what the process for that is in a second, but effectively we now have a way to tie ID functor to ID, which means that we can, at any function, pass in something that says I obey a functor and use map on it. So to understand this, you have to understand something called extension functions. This is, I don't know the other languages that might implement this, but the way that Kotlin does it is quite nice. Inside an interface, you can say anything that implements this interface actually builds these functions for these totally unrelated types. That sounds kind of scary. It sounds like monkey patching, right? But this is monkey patching where the monkey has to opt into holding the banana. So you can't affect something else's scope, like whatever you want, however you want to do it. You give it the option of affecting its own scope. And this is controlled by importing these functions into the namespace where you use them. So I've defined a method here on ID of, which we remember is just kind for ID A. So I'm saying for any ID kind, there is a method map. Now, unless I explicitly then say, hi, I'm an ID function and I really want that method map, it won't be available to me. That's where this witness comes in. So the witness is something where we basically say, run all computations inside the scope of this thing, and anything that is of a particular type that I know about, decorated in this way. So the witness will basically say, all kind for ID A actually do define a map. They can be used as functors. This is great. So how can this help? What are we actually going to do? So far we've had a bunch of what look like kind of weird compile time changes that change the lookup table of where we define functions. Arrow is the library that I'm discussing here. Arrow is brilliant. It's really cool. It's an implementation of this idea with a whole bunch of syntactical nicety. The things that I really like about it, it provides a whole bunch of building blocks for functional programming that aren't really available in Kotlin. Things like carrying, partial application, a bunch of lightweight higher-kinded types, a whole bunch of really, really cool things. It ships a whole bunch of standard containers that obey the spec that it builds up in terms of the type classopedia that it provides. So it builds options, I/O, all that kind of stuff that you get from the Haskell standard library or any of the alternative standard libraries. It has an option for that. It has a very, very rich lens and optics library. It does a ton of work around I/O and effects and async and all that kind of stuff. So it's got a very, very rich standard library. And the thing that it does that's really nice is it has a very rich type classopedia. So if you are working on something and you think, oh man, it'd be really nice if I could define applicative for this, you can. And it tells you what the shape of applicative should be. And the nice thing with that is, this is pretty much the standard FP library in Kotlin. It actually used to be 3 different libraries and they all merged, which means that you have a very good chance of using someone else's library that actually obeys this spec. So from that point of view, it's really nice. And the ergonomics of creating these type classes is quite smooth. So speaking of async very quickly, just an example of why this library is so useful. Kotlin ships something called coroutines natively. And effectively, that means that it has the ability to have deferred computation on a number of threads in the background behind developers necessary, setting up these things. You just say, hey, this is an async function, you deal with it, come back when it's ready. Performs operations in parallel, but because it doesn't have the ability to express a type like an either, if something happens and a particular coroutine goes wrong, your entire thread blows. And it's up to you to try catch that, right? This sucks. I hate having to remember, hey, by the way, this thing might throw somewhere. Now you have to deal with it everywhere you call it, or you deal with it once at the top, and you have to remember your banner. It's a nightmare. So instead, we use arrows built-in asynchronous. And effectively, the way that it works is it just decorates things that it knows are asynchronous with a particular shared interface. So the other thing that's unfortunate is in the Kotlin and in the Java ecosystem, there are probably 4 ways to do deferred computation. There's RxJava, there's coroutines, there's a whole bunch of these things. And so if you want to use a code base that has a couple of those in it, you find yourself writing the same function over and over and over and over again, manually monomorphizing. Arrow has written a couple of type classes that abstract over these things, one of which is monad defer. And effectively, we have an instance of monad defer for a bunch of these libraries, which means that you can write a function that says, I'll get a thing that defers, I'll do a bunch of stuff with it, I'll return it. And then as long as you can have a witness that says, hey, this thing is totally a monad defer, hey, this is the thing that is a monad defer, pass it into this function, you get all of that for free. And because we're being explicit about failures or explicit about types, we actually deal with these failures in line when we encounter them. So there's a function called unsafe attempt async, and these things are basically just a way of saying, hey, I force a thing to happen. It returns a type class called a try, which is like an either, where it's explicit that a throwable is the left branch. And the idea there is that you have to deal with that. You can't get the value out unless you acknowledge this is an either. I have to say, fmap to get the value, or I have to do something to deal with the left branch, or whatever it is I'm going to do. The really nice thing, and this is the kind of the sugary part, is it also ships something that's analogous to do notation. So we have something called a comprehension. And effectively, a comprehension is a way of saying execute these steps without actually executing the steps. So it will run through all of those things. It'll push them into a task queue to operate in some way, comes back to it later. You don't worry about it until you force the function to evaluate. And the idea there is that if you have multiple asynchronous things that you're dealing with, rather than dealing with them one at a time, try catching around each of them, dealing with all of this plumbing yourself, instead, you can just use the deferred operator, you can use the monad error instance, you can put up a binding catch comprehension. If anything in that pipeline of operations throws, the binding catch will catch it, store it as a throwable for that operation, and then it's up to you how you want to deal with that. You can sequence and say, by the way, if one thing fails, everything is wrong. You can just handle that one in a particular way with the default. Everything kind of runs smoothly. So let's move on to writing your own. This is kind of the meat and the potatoes. It looks cool, but it also looks like it probably takes a lot of code to kind of deal with, right? So as before, we define a type class as an interface. We're generic in some parameter. And we define abstract methods on this interface, or we define concrete methods on this interface that take advantage of other methods that are in scope. We can define default implementations based on whatever abstract implementations are needed. Now, instead of us needing to do all of the plumbing before of defining for ID and ID of and the kinds and all that kind of stuff, Arrow ships a higher kind decorator that takes care of all of that code gen for you. So it creates the kind, it creates the brand, it creates the plumbing, it does all of that stuff that ties everything together. So we take the class that we've defined in this step, where we've said we have a class ID. ID is generic in T, it belongs to ID of, and it has a companion object, and it generates out for ID, the private constructor, it generates out ID of, it generates out the fix function. So now we can use this with the type class that we've defined. We take the type class that we have, we define the methods that need to be implemented on the ID instance, and then we build an instance. So we have the instance decorator that says, take the ID class and build the companion object that is the witness, and build all the plumbing that says, by the way, these two things are the same thing, gives us all of that for free. And there are even laws to abide. So this is always a nice thing to see in a functional programming library, is not just, oh, by the way, it obeys whatever the interface we said was, but it actually obeys the laws behind the object itself. So the first law is the covariant identity, that if we call fmap with the identity function, we get back the same thing that we started with. The second law is the composition law, and effectively that is that if we call fmap on the first thing with a function and then call fmap on the result of that with a function, that's the same as calling fmap with the composition of those two functions. How cool is property-based testing? It's a really nice process. And then to use these laws, we basically ship in arrow test. It ships a helper to test laws. It takes a list of things that are defined as law. Laws are defined to give the property-based testing into the actual thing itself. And you can call each of these as you go. So enforcing, it's good practice as you build up your own instances of these type classes to test them against the laws that implement them. So just revisiting invoking via witness. So we have to pass a witness in. We've seen that before. If we actually define the method on the type class itself, then the witness is implicit. We say, by the way, this is of applicative F, so you don't need to tell me how you get an applicative F. And it handles all of the plumbing itself that way, which is quite nice. Makes a lot of sense for library functions like lift A2, maybe not so much for your specific database access. If that's still too much typing, you can derive these. So as long as you have access to where the class is being declared, as long as you define all of the methods that are needed in order to derive the class, you can just call @deriving the decorator and what class you want to derive. It'll take care of building all of that plumbing for you as well. So we have a much, much simpler process. Define a data type, write its methods, derive its instances, away we go. Just a quick callback to something that I think is actually the really, really nice aspect out of this. Effectively, we have ad hoc polymorphism defined post hoc to the language, which is really cool. But alongside that, the language itself defines a way for you to extend classes without having access to the class itself. And that's a really nice idea. Without it being monkey patching where everything kind of breaks because you both define array.reduce and now everything explodes. But it's a way of actually saying this should have this because I've now defined a new function that would be useful for a list to have. So I've defined sequence. It would be great if lists had sequences. By the way, here's how they could. And then it's up to you at any place that you use a list to say, also, I'd really like that sequence thing that I built earlier. Please use that here, which is very useful. So in closing, why? Obviously, Haskell, Scala, all of these things exist. And for a lot of us, for a lot of you, they might be very viable choices. But while this doesn't have the ergonomics or the safety necessarily of Haskell, and it doesn't have the established ecosystem of Scala yet, it's a much smaller language and a much smaller approach. And that means that it's small enough to eat one bite at a time. If you're working in a company or with a team that maybe isn't quite ready for functional programming with lenses, bananas, and barbed wire, you might have a team that's ready for FMAP. You might have a team that's ready for Functor or either. And with these things, you can actually sprinkle them over your code base very easily without needing to take the entire operation with you. Kotlin allows you to take smaller mouthfuls when you onboard people into these processes. From a completely scientific survey, and totally not just the Stack Overflow developer survey numbers, Java looked to be at least 40 times more prevalent in industry than Haskell, probably way more. Haskell didn't even make it onto the most used list, so this is just a guess at the numbers. Every Java code base has problems that were solved decades ago. So the number of null pointer exceptions on GitHub is a huge number. There's no reason for us to be writing code like that. The languages that we can get hired for easily, or that we can hire for easily, or that we can convince companies to adopt easily, aren't necessarily the ones that are fun or safe or correct. Kotlin through Arrow, through this library, makes a lot of these things available to us in a language that is sellable to business, sellable to developers who aren't necessarily ready for some of the abstractions that we're used to, and allows us to pass these things on one piece at a time. So yeah, check out Arrow, the library. If anyone's coming to the workshop after lunch, please make sure clone that repository and get started. I think the only dependency is the JDK. Other than that, it's just a Gradle wrapper project, so you should be good to go on any operating system. And I think it's in here.
It's
so, yeah.
in the blue.
Oh, in the blue room? So it's downstairs. Cool. So yeah, hope to see you all there. And yeah, please come say hi.